There are many known methods for data compression. They are based on different ideas and are suitable for different types of data. I mean, you cannot compress a song just the way you compress an image or a text. However, the core idea of every compression algorithm is based on the Claude Shannon's information theory. It quotes, "A meaningful information is always redundant." All data compression algorithms work by identifying any redundancy from the original data in the source file. Any non-random data has some structure, and this structure can be exploited to achieve a smaller representation of the data, a representation that can be considered as the basic building block of information. English is a redundant language. Here's a little test to prove the above statement. See, our brain is so good at predicting next bit, or character, of information. Shannon termed this amount of information contained in a given message as information entropy or Shannon's entropy. Shannon's entropy is defined as the negative sum of the probability of each possible outcome times the log of the probability of each possible outcome. We will discuss this formula in depth later in the video. You can learn more about information theory by clicking that little I button there. Based on how compression algorithm reduce redundancy, there are two types of data compression: lossy compression and lossless compression. Lossy compression results in lost data and quality from the original version of data. Lossy compression is typically associated with image files, such as JPEGs, but can also be used for audio files, like MP3s or AAC files. The looseness of an image file may show up as jagged edges or pixelated areas. In audio files, the looseness may produce a watery sound or reduce the dynamic range of the audio. Because lossy compression removes data from the original file, the resulting file often takes up much less disk space than the original. For example, a JPEG image may reduce an image's file size by more than 80%, with little noticeable effect. Similarly, a compressed MP3 file may be 1/10 the size of the original audio file and may sound almost identical. On contrary, lossless compression reduces a file size with no loss of quality. This seemingly magical method of reducing file sizes can be applied to both image and audio files. While JPEGs and MP3s use lossy compression, newer compression algorithms, such as JPEG 2000 and Apple lossless compression, can be used to create lossless compressed files. Lossless compression basically rewrites the data of the original file in a more efficient way. However, because no quality is lost, the resulting files are typically much larger than files compressed with lossy compression. In this video, let's talk about a very simple lossless compression algorithm called Huffman Coding, an algorithm developed by David A. Huffman while he was a SC.D. student at MIT. The idea behind Huffman coding is to assign variable length codes to input characters. Lengths of the assigned codes are based on the frequencies of corresponding characters. The most frequent characters gets the smallest code and the least frequent characters gets the largest code. For example, consider Mississippi. Each character is of 1 byte and in total this word costs 11 bytes. We will make a frequency distribution table of each character and then make a Huffman tree, which is a full binary tree. First we take characters with lowest frequencies, that is, M, with frequency 1, and P, with frequency 2. Then we insert into the tree, where the parent node is the sum of frequencies of both characters. Then we take the next two least frequent characters and do the same. Repeat this process for each discrete character. Finally label each left path as 0 and each right path as 1. Now we are ready to assign a discrete code for each character. We do it by concatenating the labels of paths to reach that character in the Huffman tree. P is 111, M is 110, S is 10, and finally I is just 0. This is called codebook. Using codebook we now encode Mississippi as 110101010101010, which takes only 18 bits or around 2 bytes. But this bit stream is useless without the codebook, so we append our codebook in beginning of the code, and the combined size is just 7 bytes, which is lot better than the original 11 bytes. We can calculate the performance of the compression algorithm using compression ratio and compression factor. If you have seen famous American comedy TV series, Silicon Valley, you may recognize compression factor as Weisman score. So, Huffman algorithm's Weissman score for our particular case is 1.57. There are also other factors on which our compression algorithm is judged, such as compression gain, cycles per byte, peak signal-to-noise ratio, which we will discuss in later videos. If you're still around, please leave a like and post a comment with your feedbacks and questions. And don't forget to subscribe and press that bell icon so that you won't miss any of the future videos of this series called Data Compression 101.